Hi everyone. Now, let's say I would ask you to take the limit of this function as it approaches this point. Now, ordinarily you would be thinking, good sir, this limit doesn't exist, and you would in fact be right. But this is where we introduce the concept of one-sided limits. So what a one-sided limit is you're basically taking the limit from one and only one side, as the name somewhat implies. So, let's take, well, as you may have noticed, as we approach our function from the positive or the right side, you see it approaches this number, L1. So, the limit as f of x approaches, let's say c, from the positive side, is L1. But as we approach c from the negative side, it's equal to L2. So the proper notation for this would be, as our function f of x approaches c from the positive side, it's equal to L1. And, or, really, as our function f of x approaches c from the negative side, it's equal to L2. So that, in essence, is one-sided limits. Now moving on to continuity. The golden rule of continuity is if it's a connected line, it's continuous. Or if you want to think of it another way, it's possible to draw the function without ever lifting your pencil. A very philosophical view, I believe. But yes, moving on. The more precise mathematical definition for continuity. So a function is continuous at x equals c if and only if f of c exists, the limit of f of x as x approaches from the positive side exists, the limit of f of x as x approaches from the negative side exists, the limit of f of x as x approaches c is equal to f of c. Now, this is actually incredibly confusing, or more confusing than it should be, and calculus, as we all know, should never be confusing. So, a much simpler way of looking at this is a function is continuous at a point x equals c if f of c exists, and if the limit of f of x as x approaches c is equal to f of c. So you should remember this, but I'm going to replace this with our simpler rules. If you guys don't. That doesn't seem to be it. 3, 1, 2. Okay. Our simpler rules. So, here are 4 examples of functions that are not continuous. So, let's look at our first function. As we can see, everything's pretty wonderful until we get to this point, where we have a hole. And our first rule in our simplified rules is that f of c must exist. Since f of c doesn't exist, well, this function is clearly not continuous. However, we can now define a hole, because as we see a hole, the limits exist, or the limit exists, but regrettably the point doesn't. So now, let's look at this function. Now, everything seems to be wonderful until we get to what seems to be the same problem, but we can't say that f of c doesn't exist, because it does. It's just up here. But let's look at our second rule. Our second rule says that the limit of f of x as x approaches c must equal f of c. And that's clearly not the case. As f of x approaches c, it equals to this number. But f of c is way over here. So clearly, this function is also not continuous. Looking at this function, everything's pretty wonderful until we jump. Now jumping usually is a pretty wonderful exercise, but in mathematics, or in this case calculus, it's not wonderful in the sense of continuity. Because obviously, even though f of c exists, the limit as f of x as f approaches c does not exist. So this function is not continuous. And in this function, we see a vertical asymptote. And in this case, neither f of c nor the limit of f of x as x approaches c exist. So this function is not continuous. Now the last thing we need to do is, well, let's take an example actually. And if you believe that you don't need this example, well then feel free to skip to the very end. But I do cover something that's relatively important involving absolute functions. So I have this problem. I want to find the limit of this function as x approaches 3. Now, you might have noticed the absolute value sign. And as regrettably, we can't just wade directly into this problem because calculus, as far as I know, or at least in APBC calculus does not like absolute value functions. So our goal is to try to replace this absolute value with a piecewise defined function. So if you look at our very conveniently placed graph here, not only is our function not defined at x equals 3, but it also changes signs when x is greater than 3 and when x is less than 3. So let's make a piecewise defined function. Poof. Now, as you can see, when x is greater than 3, this function is equivalent to x minus 3 over x minus 3, which in this case is always equal to 1. However, when x is less than 3, this function is equivalent to x minus 3 over negative x minus 3, which is always equal to negative 1. Now what we can see from this is that the limit as x minus 3 over absolute value of x minus 3 as x approaches 3 does not exist. However, we can make one-sided limits to describe this situation. So, in this case, since when x is greater than 3, the function is always equal to 1, we can see that the limit as x approaches 3 from the positive side is equal to 1. And when x approaches 3 from the negative side, it's always equal to negative 1. So what you basically wanted to grab from this lesson is this. You want to remember the rules for continuity. Although it would be easier to just go back and remember the simplified rules, you should remember the 4 formal rules, which is that f of c exists, the limit of f of x as x approaches c from the positive side exists, the limit of f of x as x approaches from c from the negative side exists, and the limit of f of x as x approaches c is equal to f of c. You also want to remember that one-sided limits are limits that approach from only one side, which is either the positive or the negative side. And finally, even though this technically isn't part of the lesson, or isn't an essential part of the lesson, you want to remember that taking the limit of absolute functions usually requires changing an absolute function to a piecewise defined function. In fact, I can't think of an instance on the top of my head in which case you would keep an absolute value function the way it is. Alright, so thank you, have a nice day.